Okay, now we want to determine the circuit model parameters. Okay, the equivalent circuit of induction motor is a very useful tool for determining the motor's response to changes in load. However, if the model is to be used for a real machine, it is necessary to determine what the element values are that go into the model. How can we measure the R1, R2, X1, X2 and also Xm for a real motor? Okay, so these pieces of information may be found by performing a series of tests on the induction motor that are analogous to the short circuit and open circuit tests in a transformer. Okay, so the test must be performed under precisely controlled conditions. Since the resistances vary with temperature and the rotor resistance also varies with rotor frequency. So the exact detail of how each induction motor test must be performed in order to achieve accurate results are described in IEEE Standard 112. Although the details of the tests are very complicated, the concept behind them are relatively straightforward and will be explained here. Okay, why it is important is because we want to we want to determine the torque speed curve of a real induction motor. So these are the parameters that we want to look for. Okay, there are several tests. Okay, so we will try to supply with DC test. So when we supply DC test, we can find the stator resistance. Okay, and then the no load test. So what we want to look for is the impedance of no load. Okay, during the no load. So you can find the X1 and X1 plus Xm. Okay, and then the log rotor test. So this is three kinds of tests. What we want to look for. Okay, we go first to the DC test. Okay, this is a little bit simple. When we change the we supply the DC voltage to the induction motor. So since there are three connections, okay, so you can see the Y connected something like this. So okay, so this is Y connected. So we just put DC. So since DC have only two, so we connected like this. Okay, for example like this only. So we connected at 2 points. Okay, we just connected 2 points. So similar like this. Okay, so we supply a DC voltage and then we put some ammeter and also we put the voltmeter. Okay, so why we need to limit the current? Because not limit the current, we want to vary the current until that the current flow up to the rated current. Okay, similar like during the using the AC. So we try to make sure that the I flow is at rated. Okay, so since there are two lines, okay, so the voltage over here, okay, the current flow, so voltage is represented like this. So voltage DC, okay, actually is measured two resistor, okay, I to R. Okay, so for now we can measure the R. Okay, so now we change again to R1 is equal to VDC over I. Okay, so now we can measure the value of R. Okay, since the DC does not induce, so the rotor is not moving. Okay, and I adjusted to the R rated voltage between the terminal measure. So this is what we will get. So this is the easiest way. So we will get the value of R. Okay, so where the V DC equal to 2I. Okay. Okay, for the no load test, okay, the no load test of induction motor measures the rotational losses of the motor and provide information about its magnetizing current. Okay, so this is important keyword. Okay, the test circuit of this test is shown in the figure. Okay, okay, so this is the equivalent circuit of the induction motor. Okay, so we will put some voltage, the voltmeter between the two lines, and also the wattmeter, and also the current. Okay, the ammeter. So we want to measure the current. Okay, so this kind of things, when we supply the voltage, okay, we supply the voltage, the three-phase voltage, and the motor will rotate freely. Okay, so the only load on this motor is the friction and windage losses. Okay, so all converted, P converted. Okay, so P converted is a mechanical lah. Okay, the mechanical is equivalent to the mechanical losses. Okay, contribute to the mechanical losses. Okay, mechanical losses. Okay, for example, and the slip of the motor. Okay, the slip. Okay, the slip right now is very slow. Very small. Okay, the slip. Okay, the slip is very small. Nearly to zero. It's around 0.0001. Oh, sorry. It's around 0.001. Okay. I can say it's close to zero. Okay, or maybe less. Or maybe less. Okay. So the equivalent circuit of this motor. Okay. So since this is the S is very small, so this component will be very high. Okay, so the power converted. Okay, the power converted contribute to this most of the power. Okay, most of the power actually come from this, because this is too high. Okay, because this is high, so this is high than this one. Okay, these two. Okay, so that we can assume the R2 and also JX2 we can ignore that part. Okay, this is because of the R2 1 minus S divided by S. This component is very high. Okay, so the power measured is equivalent to contribute more to this point. Okay. Okay, from the current equivalent circuit. Okay, from the current equivalent circuit, we can see that the rotor losses. Okay. Okay, the output of resistor in the parallel with the magnetizing component. Okay, this is parallel. So this tree is parallel. Okay, so this is the losses. Okay, the magnetizing component XM and also the copper losses. Okay, RC. Okay, in this motor at no load condition, the input power measured by the meter must equal to the losses in the motor. Okay, so the power over here, the power wattmeter over here measured must be equivalent to the losses, motor losses. Okay, the rotor component, the rotor copper losses are negligible. Okay, this is because the current I2 is extremely small. Okay, so the current flow here is I2 is very small because the resistance is very high. Okay, and also this one we can negligible. We can negligible because the power is transferred to the power measure is contribute from this one. Okay, So the current flow, I can say that current flow is directly to the magnetizing current, okay, magnetizing component, okay. So that the R2 is negligible, okay. So then the stator copper losses are given. So this is the stator copper losses, okay. So I think you know before. Okay, so then the power. So this is the power. This is the power input, power measured is equal to power stator copper losses plus the power in the rotational. Okay, so what is the power rotational? Is the core, friction and windage, and also miscellaneous. Okay. Okay. So then we can get the new equivalent circuit. Okay, so we can delete over here. Okay. Okay, since the currents flow directly to this magnetizing component, okay. So since the losses over here or the resistance over here is too high, and then the current flow directly to the magnetizing component. Okay, we assume directly component. We assume directly move to this component and will produce the very high current. So high current is needed. Okay, the high current is needed to rotate the motor. Okay, because to generate the magnetizing to magnetize the field. Okay, so that the current also will be higher to the magnetizing current. Okay, so the magnetizing component, okay, XM can say that will be much smaller than the resistance in parallel with it, and the overall input power factor will be very small. Okay, so with the large, okay, since this current is very large, okay, and also go through the reactance component, okay, so we call it as a or the lagging current. So the current is lagging current is very high. So most of the voltage drop will be across the inductive component. So the voltage drop will be at the inductive component. Okay. So the equivalent circuit, the equivalent input impedance in does approach approximately. So since the current actually flow is very high to the magnetizing to the reactance, okay, to the inductive component, and the current is lagging near to the inductance. So the R1 over here can be negligible also. Okay. So due to the large lagging current, so voltage drop will be across the inductive component. So the voltage measure over here. So okay, so we can find it like this. Okay, so the I1 over here is the average current in the three lines. Okay, and the voltage over here, okay, the voltmeter over here is a line voltage. Okay, so we need to transfer to the phase voltage. Okay, so what we get over here for the inductance is equivalent to X1 plus XM. Okay, is equivalent to this part and this part only. Okay, please be remembered that this kind of calculation or measurement is I can say they have a lot of assumption. Okay, however the correct or the correct calculation or the correct parameter will be similar to this whatever we use. Okay, the assumption. Okay, the third test can be performed on an induction motor to determine its circuit parameter is called the lock rotor test, or sometimes the block rotor test. Okay, so this test corresponds to the short circuit test of on a transformer. Okay, in this test the rotor is locked or blocked, so that it cannot move. A voltage is applied to the motor and the resulting voltage, current, power are measured. Okay, so we supply the voltage, we measure the current, okay, and we also measure the voltage and also the power. Okay, and then we lock the rotor. So what happens when we lock the rotor? So the rotor is not moving and M is equal to 0, then slip become 1. Okay, so at this point also the frequency, so if you still remember, the FRR is equal to S FE. Okay, so now FR is equivalent to FE equivalent to F test. Okay, so the I rated, so at this point the I measured is the full load current. Okay, so this is the rated current. Okay, so since the value of R over here, the S is equal to 1, so since S is equal to 1, then the component, the losses over here, okay, the value of R I can say is very small. Okay, so when there are too small, okay, when this is small, so the X2 also I can say is very small. Okay, so that all the current will flow directly to this component. Okay, so in the equivalent circuit, okay, because since the rotor is not moving, so the XM component over here will be very high. Okay, so since the reactance over here is very high, so the current flow over here is like too small, or we assume that no current flow over here, so the current will directly flow to the X2 and R2 component. Okay, so we can say over here the XM, okay, the XM is very large, greater than R2 and plus JX2, similar to the XC. So this point we negligible, will neglect. Okay, so we assume that the current flow directly to is like a series. Everything is like a series. Okay, so however, there is one problem with this test. So during the normal operation condition, the S of the motor is only 2 to 4%, and the resulting the F rotor is in the range of 1 to 2 Hertz. Okay, so the operating frequency, okay, the FE rated is around 50 to 60 Hertz. Does not represent the normal operating condition of the rotor. Okay, a typical compromise is to use the frequency. This F test is around 25% or less of the FE rated. Okay, so later on we will need to consider the value of frequency to measure the impedance. Okay, so since the circuit is the equivalent circuit is become series, I draw again. Okay, so we have R1, X1, and then we have X2, and then we have R2. Okay, so R1, X1, X2, and also R2. Okay, so we can directly measure. So this is from the voltage voltmeter. So the power in is equal to this is from the wattmeter. Okay, the square root of 3 V line times I line cos theta. Okay, so then we measure the magnitude. So the magnitude of the total impedance, okay, so equal to V phase. Okay, divided by I line. So we convert the V phase, okay. We convert the V line to the V phase, okay, become this equation, okay. So the total impedance will be Z log rotor, so it will be equivalent to R1 plus R2, okay, plus J component of X1 plus X2, okay. So over here they write a prime over here. You can see they write a prime is because it's dependent on the frequency, okay. So this is how to measure the so if you want to measure the R component, so R is equivalent to ZLR cos theta. So this is from the imaginary and real components, okay. So this one is XLR, so this is X prime, so ZLR sin theta, okay. So the R log during the test, okay, log rotor test is equal to R1 and R2, okay. From here we can see that R1 we found during the DC test, and from here we can get the value of R2, okay. So this is from the DC test, okay, DC test. So we can measure, we can find the value of R2, okay. So this is LR prime equal to XI prime, okay. So over here is prime, sorry, okay, prime, because it's dependent on the frequency. So to convert it, the XR LR is equal to F rated, okay, divided by F test, okay, multiply with the X prime LR, okay. Then we will equivalent to X1 and X2. Okay, unfortunately there is no simple way to separate between these two, okay. To separate the contribution of the stator and rotor reactance, okay. So this is the stator reactance, and this is the rotor reactance, okay. So over the years, experience has shown that motor of a certain design type have a certain proportion between the rotor and stator reactance, okay. There are several tests and also the design. There's some design. So some design they mention that X1 is equal to 0.5 XLR, okay, and X2 also become the same, okay, divide by 2, okay. So this is the simplest design, okay. This is the simplest way to use. So I think in this course, I think better we use at this point only, or unless we give you the condition, okay. For example, during the question or so on, we mention that the X1 is equal to 0.4 XLR, okay, for example, and the X2 equal to 0.6 XLR, okay.